Hello, my name is Sung-Tek Lee, and this is Physics 2212 Lab 5 report. The purpose of this lab is to apply Faraday's law by conducting an experiment of dropping a bar magnet through a conducting tube. There's two fundamental principles I'll be using. The first one is the Biot-Savart law, which calculates the B field, the magnetic field, and Faraday's law, which will be calculating the d flux dt, and we will use this Faraday's law to calculate the magnetic force. To give a brief overview for the results of the experiment, for the experimental average time of the magnetic falling through the tube is 1.22 seconds, and the computational average time calculated was 1.269 seconds. The system for this experiment is the bar magnet and the aluminum foil tube. The surroundings is everything else except the magnet and the tube. And for this experiment, I made some assumptions such as neglecting air resistance of the falling magnet and neglecting external magnetic field besides the falling bar magnet. And I also assumed that there is a uniform gravitational field. These are some measurements I made for the experiment. The length of the tube was 0.26 meters, and the width of the tube and the inner radius was each 0.007 meters and 0.028 meters. So the total radius will be the addition of these two measurements, which is 0.035 meters. The mu value is from lab5, which is 1.995, and the mass of the magnet was measured to be 0.025 kilograms. So on this right-hand side of this slide, we can see a table of 5 trials of dropping the magnet through the aluminum tube, and the average value was calculated to be 1.22 seconds. So before I move on to the computational model, I'll answer these two checkpoint questions. The first question, why can't we use a steel pipe? In this case, since the steel pipe can be attracted to magnets due to its iron material, there could be an induced magnetization, and this could create an additional variable of magnetic fields that would complicate the experimental results. So I suspect it could make it fall more slowly or faster. Well, in conclusion, this will complicate the experimental results and result a different value. And what happens to the magnets? How does this compare to magnetic falling in free space without a tube? A magnet falls slower through a conductive tube due to opposing magnetic fields from induced currents, unlike in free space where it falls freely under gravity. So in other words, the time measured will be a lot slower than a free-falling magnet. And I'll move on to computational model. This is my V Python code. And as you can see, these are the measurements I made for the experience, which I will use our input values for this whole V Python code. And as you can see, this function dipole B is to calculate the magnetic field. And this line of code, as you can see, is an application of the Biot-Savart's law. And this function is to calculate d flux dt analytic, which we can find in this line of code. We use the Biot-Savart law in this case. And we will consider two forces, which is the gravitational force and the magnetic force on the magnets. And in these lines of code, we use to update the magnetic velocity and position. So if I run this program, I have this image of a magnet falling, and as you can see in this graph, shows that the velocity increased as it falls down, and this computational model resulted in displayed an average time of 1.269 seconds. So it was slower, but not really much different from the experimental results. So why does this discrepancies happen? Is the possible reasons could be the measurement error or the alignment of the magnet in two. And I might have not stopped the time warp exactly at the moment the magnet hit the floor. And there could be also some errors or discrepancies happen by my assumptions, which is neglecting external magnetic fields and air resistance. And I'll conclude my lab report by answering these what-if questions. For the first what-if question, reducing the resistance as close to zero would increase the current by Ohm's law, I equals V over R. And this would cause the magnet's speed of falling slower, which will result in increased average time of falling. For the second one of questions, the holes in the tube will reduce the strength of the magnetic force and currents, which will lead to making the magnet to fall faster. Thank you.